University Video Communications is pleased to present this videotape edition of the Distinguished Lecture Series, Industry Leaders in Computer Science and Electrical Engineering. Speakers and topics in this series have been nominated by university faculty who want industry material for use in their courses. Today's presentation, Parallel Processing, is by Tilak Agerwala. An IEEE Fellow, he received his Bachelor of Technology in Electrical Engineering from the Indian Institute of Technology and his PhD in Electrical Engineering from Johns Hopkins University. As a member of the Corporate Technical Committee in the Science and Technology Department at IBM Corporate Headquarters, one of his current responsibilities is for corporate-wide assessment of parallel processing at IBM. UVC is happy to introduce to you Dr. Tilak Agerwala.
It's a pleasure to have this opportunity to speak to you on one of my favorite topics, namely parallel processing. The presentation today will be a tutorial presentation where I will try to give you an overview of some of the important trends in this area of parallel processing. Now, many of you are quite familiar with the various motivations for parallel processing. I would, on this particular slide, emphasize two. The performance potential of parallel processing is one of the key motivations, and the performance aspects really come in two flavors. One can talk about the maximum performance possible, the maximum absolute performance. One can also be motivated by the ability to pack a lot of performance in a small package, and one typically may want to do that in workstations. There is a potential for improved cost performance, to provide scalable performance, and the other one on this list that I really do want to emphasize is reduced development cost. And reduced development cost also comes in two flavors. Sometimes it's possible to get significant performance without developing very sophisticated technologies and very sophisticated packages that are developed for very high performance machines. Secondly, if one is interested in really providing a very wide range of performance, for example, in IBM, we cover the range of systems from personal computers to supercomputers. Then one is faced with the question of how many unique uniprocessor designs should one develop to cover that range of performance. And clearly with parallel processing then, one has an added dimension so that the number of unique processor designs can be reduced and the range can be covered with the use of parallel processing. Increased availability is also an important consideration and is very important in today's systems. There has been a huge amount of progress in computers generally. I'd just like to state that the driving force behind much of this progress is really progress in microelectronics. And this slide illustrates what some of the trends are in the area of memory, CMOS, and bipolar technologies. Now, I should emphasize that this slide is not just obtained by sitting down with log paper and projecting into the future by drawing straight lines. This graph is obtained by a very thorough evaluation of the problems that are likely to be faced in the future, and by considering the solutions that one may use to address some of these problems. And the basic message that I want to give you on this slide is that technology at this level is going straight ahead and there's no end in sight. Now, this technology, the basic technology capability, for example, then translates into the ability to build processing systems. And what I'm illustrating on this slide is the evolution of microprocessor systems, that is systems that can be built on a single chip or on a small collection of chips. And with 1 micron CMOS technology today, we are essentially sitting in the range of 20 to 30 million instructions per second, and this will steadily move into the 50 to 70 range, I should emphasize that this performance comes, these numbers are based on the assumption of having a machine organization that can deliver approximately 1.2 cycles per instruction for average workloads. If one uses more sophisticated machine organizations, and we certainly know how to do that, these numbers can increase significantly. Furthermore, another factor of 2 can be obtained by using liquid nitrogen cooling and by using some of the developments in high density, low power bipolar technologies. It's certainly feasible in the early 1990s to get into the 100 million instruction per second range. Now, I really want to make 2 points over here. Firstly, that the building blocks that we have available to us now are becoming powerful enough so that the small MIPS effects that one would encounter with lower performance microprocessors are no longer coming into the picture. And secondly, that with a 40, 50, 100 million instruction per second building block, one does not have to go to very high levels of parallel processing to get fairly significant systems. So 16-way and 32-way parallelism with a 100 MIP microprocessor puts you into a very interesting range. Of course, to get the supercomputing kinds of capabilities, as I will point out, one can use higher levels of parallelism. Now, let me then talk about some of the important trends in parallel processing. And this slide will indicate to you that I am, in fact, viewing parallel processing in a very broad sense to cover clustering, multiprocessing, and very highly parallel processing. And I will spend the next few minutes defining these terms and giving you some examples of systems in each of these areas. In clustering, one typically connects a number of complete computers, that is, processor and memory pairs, together to disks. And the key sort of motivation for clustering is to obtain improved capacity and improved availability, yet at the same time to provide a single system image. That is the key challenge. That is, one is trying to develop a system that consists of multiple processors, but looks like a single computer system to the operator and to the end user. Now, what do I mean by single system image? I basically mean the following, that the system should look like one computer system from an administrative point of view. It should have a single file system. Users who log on to the system should not be aware of the particular computer that they end up executing on, and the system should provide a high degree of availability and graceful degradation. Now, in clustering, this is attained not by having one single operating system that executes on all the machines, but rather by having multiple copies of the operating systems that exchange information typically at the page level, and thereby software synchronization techniques are adequate. Let me just point out that examples of clustering are the Transparent Computing Facility, which is part of IBM's Unix systems, and I will talk about that later. Systems like Tandem and VAX Cluster are also examples of clusters. Now, the situation in multiprocessing is a little different. Here, you have processors that share information at very high speeds, typically by executing loads and stores against a single memory system. The synchronization between the processors is provided at the hardware level because they exchange information at these very high speeds. As a result of this hardware synchronization, the extensibility is typically limited. So these systems are restricted to the 8, 16, 32 processor range and typically will not go significantly beyond that. Now, the goal here really is to get the multiprocessor to look and behave exactly like a uniprocessor system. So all the subsystem interfaces, all the application interfaces to the operating system should be identical to what they are in a uniprocessor. And this really means taking a uniprocessor operating system and having this single operating system execute across the multiple processors. And this involves implementing mutual exclusion. It involves analyzing the data structures, understanding how they're used, and providing the appropriate levels of process synchronization. The key, of course, is to do all of that and yet obtain very high efficiency. Now, multiprocessing is being applied across a very wide range of systems, all the way from workstations to high-end machines. The motivations in each case are slightly different, though, of course, they are all related. In high-end systems, the overall goal is to provide levels of performance beyond that achievable by the highest performance uniprocessor at any given point in time. So the key high-end issue is really performance. All the other issues and motivations that I talked about earlier do apply as well, but the performance issue, I believe, dominates. In the mid-range, again, performance comes into the picture, but the goal here is really to provide high levels of performance without necessarily getting into very high performance uniprocessor development, without getting into the high performance technologies and packages that characterize very high performance uniprocessors. And at the same time, horizontal growth is a key issue in the mid-range. Now, the workstations, the motivation is to provide the highest levels of performance in a very small package. And there's really a fairly interesting trend that is taking place in the workstations, which to a large extent is driven by this technology of parallel processing. And the situation is as follows. By taking some of these high-performance microprocessor systems that are in the 20, 30 million instruction per second range and implementing then a system consisting of 4 or 8 microprocessors, one can get into performance ranges that were typically characteristic of supercomputers of a few years ago. Now, the workstation, however, has an additional capability. These MIPS can also be used to provide graphics and to provide user interface processing. And since the computing engine is now very close to the user interface, they can be connected together by very, very high bandwidth interconnects, and you can typically now get levels of interactivity between the compute engine, which is in the workstation, and the graphics processor, which is in the workstation, significantly beyond what is possible by having a thin pipe that connects your workstation to a supercomputer in the background. So this is a key trend that is happening in the workstation arena, which I think is being driven significantly by this technology of parallel processing. Now, let me just give you a few examples of systems in these areas. In the high end, IBM 3090 mainframes are multiprocessors, as are the Crays, and as will be the SS1 machine from Steve Chen's company. In the mid-range, the machine systems like the 4381, Alliant, and Convex are examples of systems that use parallel processing. And at the workstation, we see numerous systems today. Examples are Ardent, Stellar, and Silicon Graphics. Now we move on to the area of highly parallel processing. As many of you are aware, there's an incredibly large variety of architectures and systems that are being developed and studied both in universities and in the industry. And it is not my intention here to go into a very complicated taxonomy that describes these various parallel processors. What I would like to do, though, is take these highly parallel processing systems and put them into two sort of very general categories that I call specialized and multi-purpose. And let me just make a few comments about each of these. In the case of specialized parallel processing, the technology is very well understood today, and highly parallel specialized processors today are being used to solve important problems that are either economically important or of scientific importance. And I will talk about two examples that we have developed and are working on in IBM, the logic simulation machine and the GF11. The characteristic of these machines is that they are intended to solve just one single problem or one single well-understood algorithm, and as a result, you don't require very sophisticated programming environments and compilers. This allows you to develop these machines without great development costs. It's my estimate that machines that can deliver hundreds of gigaflops or even a teraflop are quite feasible and will be used over the next few years, and such machines can have a very significant impact on science and on engineering. But I would like to make another point, which is that there are other specialized machines, and I've given you one example on this slide, the database machine, which is a little different from a logic simulation machine or a machine for a physics application. These may be used by very few people, but a machine that can do a complex query very rapidly is performing a specialized function, but it's performing a function that will be important to a very large class of users. In fact, I believe this is an example of a more general trend where clearly subsystems are being identified, and database is one of them, which are often accessed by through very well-defined interfaces, for example, a SQL query, which are amenable to being addressed by special hardware. In the case of SQL machine, by a highly parallel processor. And this is an important trend because it's a specialized function, but it's a function that will be of use to a large number of people. So I think the whole area of specialized highly parallel processors is an important one, and we have to start understanding the role that these machines will play in general computing environments. Now, on the other hand, the area of multipurpose parallel processing, though it has significant potential, I believe is also an area where a significant amount of research still remains to be done. I will talk about this a little more later on when I describe the RP3 machine that we are working on at IBM. I would like to make 2 points at this stage, though. One is that the availability of hypercubes has really been very important. The second point I would like to make is that in my estimate, the area of data flow computing is very important because it provides the potential to exploit massively parallel, unstructured parallelism. I believe more work needs to be done in this area, but the potential is very significant. And to sort of end this introductory section, let me just say that in addition to the various classes of machines, there are two uses of parallelism, two high-level uses of parallelism that we should distinguish between. One of them I have called system parallelism, and this is the ability to take different users' applications or different database transactions and run them in parallel. This does increase throughput. It doesn't make any single application run faster. A big advantage is that it requires no change to user programs, and typically this class of parallelism is obtained through multiprocessing and through clustering. The other kind of parallelism is application parallelism, and here the goal is really to take a single job, a single transaction, or a unit of work and break it up into little pieces and run all these pieces in parallel. This doesn't make any individual application run. This does make individual applications run faster. It may not increase system throughput, and it may require changes to the user's program. Typically, multiprocessing and highly parallel processing have the potential to provide this kind of parallelism. And this sort of indicates also why multiprocessing is a very important systems trend, because it does address both system parallelism and application parallelism. What I would like to do next is to illustrate some of the concepts I've talked about with specific examples. I've chosen examples from IBM because those are the ones that I'm more familiar with. So we start off with clustering, and as part of IBM's Unix offerings, and IBM Unix is called AIX, we have a system called the Transparent Computing Facility. This system provides a single system image of the type that I had discussed earlier across heterogeneous processors. The processors can be either System 370 machines or PS2 machines. Now, single system image in this case means what I had said earlier. That is, you get a single file system, you get logon transparency, you also get a certain amount of local remote execution in a transparent manner. For example, you could be developing and editing your program on a workstation. The program could be compiled on a mid-range 4381 or 9370 and could be executed on a high-end 3090 system, and all of this would happen in a manner transparent to the end user. The second important point is that these systems can be connected in a variety of ways, either through channel-to-channel attach or using local area networks. Let me move on now to mainframe parallelism. And let me talk about the 3090 Model 600, which is a 6-way tightly coupled multiprocessor. These processors have caches, and there's very extensive hardware cache coherence that is provided in a system like this. The boxes labeled SCEs are storage control elements and are very complex switches that bring the processors and the channels together and provide a coherent view of the shared memory system. Now, in many ways, in a system like this also, some of the key challenges and some of the key issues are really software issues, and we have made a tremendous amount of progress in obtaining true symmetric multiprocessor capability in our MVS and VM operating systems. Furthermore, this multiprocessor capability is exploited by subsystems like IMS and CICS to get system parallelism. We have made extensions to the Fortran language, and together with automatic detection of parallelism, we can now exploit application parallelism across this 6-way tightly coupled multiprocessor. There's been a fair amount of work on subroutine libraries for our vector machines, and these subroutine libraries are now being extended to provide support for parallel processing as well. So the point I want to make is that the 6-way, for example, in this case, 6-way tightly coupled MP is a very well understood technology that is being exploited both for system parallelism and for application parallelism inside IBM. Just to give you a brief example of the kind of speed-ups that we are capable of getting by the use of parallel Fortran. Here's a slide that shows 3 applications with sort of varying degrees of utilization, but you can essentially get 4 to 5.5-way speed up on a 6-processor system. Another system that we are working on, which is an experimental prototype, is a combination of concepts, and we are calling it firm coupling for the lack of a better name. This is really taking 2 3090-600 complexes and connecting them at the shared electronic level with very high bandwidth fiber optic interconnections. This, as I said, should be viewed as an exploratory system, and we are trying to understand the various ways in which it can be used, some of which I have listed on the slide. So You could use one side of the system for application parallelism, the other side for system parallelism, or you could use both sides for application parallelism, or you could try to take one job and split it across all 12 processors and get application parallelism across 12 processors. We are using the system to address some of the operating system and compiler and language issues that would be involved in firm coupling. Let me move on to workstation parallelism. We have developed in research a vehicle which is again an experimental vehicle to understand some of the important issues in this area. In this particular case, what we would like to do is we would like to study how best a parallel workstation can be used, how parallelism can be used and exploited in a workstation. Again, there are various forms of parallelism that one could exploit, either the system parallelism or the application parallelism. And this is a vehicle to start studying some of these issues from a software point of view. The vehicle consists of 8 IBM RISC microprocessors, each with floating point capability and each with about 8 megabytes of memory. There's 32 megabytes of shared memory capability. This machine does have a shared address, a global address space. The memories and processors are connected together by a high-speed 80 megabyte per second bus. Again, since this is a research vehicle, we have provided a real-time hardware monitor that will allow us to make measurements on various parts of the system as the software is executing. Let me now move on to the area of highly parallel processing, and I will start with specialized highly parallel processing, and I will go through very briefly 2 examples, the engineering verification engine and the GF11 parallel processor. Now, what was the problem that we were trying to address with EVE, the engineering verification engine? The problem is really that of logic simulation. And in this particular case, the goal is to simulate the logic of a high-performance processor, one of our high-end machines. And logic simulation is a very important part, and it's a front-end part of the design process. The goal is the following. The goal is to try to simulate at the logic level a processor yet to be designed, which is in this case approximately 300,000 gates, and to simulate 5 minutes of execution of that processor that remains to be designed. Now, to do this, this was a problem we faced in the late 70s and in the early 80s. And basically, to simulate the next generation high-end machine for 5 minutes would take a 1980 mainframe approximately 100 years. And this is obviously impossible. The EVE machine will do this in 6 weeks. And so this is this is an important example of how you can use parallel processing to take a problem that is an important design problem, which is essentially impossible, and to make it very practical. And that's what EVE achieved. It achieved this by using a highly parallel processor, but a very specialized parallel processor that consists of 256 elementary processing elements connected together by a crossbar switch. Now, each of these processors, these elementary processors, is really a very simple computing element, and what it does is to read from an instruction memory and then do very simple logical operations on a data memory, and it does these operations one at a time. That is, it will take 4 data items, do a logical operation on them, and produce a result which either goes back into a local data memory element or goes across the crossbar to one of the remote processors. So it's a very simple architecture conceptually. And the key, of course, is the following. The key is to avoid the bottleneck of event-driven simulation and to take a logic network and actually compile it onto this simple parallel structure. Again, some of the key problems are really in the software compilation. These problems were addressed and solved and we were able to meet the overall goals of logic simulation that we started with. The engineering verification engine, as the slide says, has a peak rate of about 2 billion gate simulations per second. It is operational at several IBM locations. Some of these machines have 256 processors, some have less. The smallest one has 64 processors. And this is possibly one of the earliest production uses of a highly parallel processing element. We have been using these EVEs for a few years now in our development laboratories to do logic simulation. The second problem is different. The second problem is a scientific problem, and it's the problem of quantum chromodynamics. The theory of quantum chromodynamics deals with the forces that exist inside the nucleus at the quark-anti-quark level. So there's a chromoelectric field that is hypothesized to exist, which is very similar to the electrodynamic field that exists between electrons and the nucleus. The chromoelectric field exists inside the nucleus. QCD gives you the transition probabilities between quark and anti-quark configurations at various points in space and time. From these transition probabilities, from first principles, one can compute the mass of the proton. So the goal is to compute the mass of the proton, which is a known quantity, and to see whether the computation matches what we know the mass of the proton to be. If it does, then we have a certain amount of confidence that QCD is correct. If it doesn't match, then we know that QCD is wrong. Now, this is a structured and regular computation, but the physicist involved with this particular theory at IBM estimates that 3 times 10 to the 17 operations would be required to compute the mass of the proton. On a machine that could sustain 100 megaflops, this would take 100 years, and again, is quite impossible. On the GF11, this problem can be solved in approximately 1 year. This is another somewhat dramatic example of the use of parallel processing to take an important problem, in this case an important scientific problem, and bring it into the realm of possibility, a problem that for all practical purposes today is intractable. The GF11 architecture is an SIMD architecture. That is, there's a central control that broadcasts instructions to 576 processors. Now, each of these processors is a fairly powerful machine. It's not a little microprocessor. Each processor has the capability of executing 20 megaflops, that is 20 million floating point operations per second. It can do I/O at the rate of 20 megabytes per second, and it has the capability also of doing 20 million fixed point operations per second. If you multiply all that by 576, you end up with over 11 gigaflops, over 11 billion fixed point operations per second, and a total bandwidth of 11 gigabytes per second. Now, it is not our claim that you can get that level of performance on any arbitrary problem, but we do believe that on QCD we can get up to 90% utilization and therefore can sustain a computation rate of 10 gigaflops per second, which would be required to solve the QCD problem and compute the mass of the proton in approximately 1 year. The other important feature of this machine is the interconnection network. The interconnection network works as follows. You can select, before you start the problem, you can select up to 1,000 of the factorial 576 possible permutations. And then you can actually provide each one of these permutations every 200 nanoseconds at execution time. Now, QCD itself does not require that much generality for the computations. Yet this permutation network and the ability to have these various permutations is important because you want to be able to separate the physical interconnection of the processors from the way they are used logically. And this is important if you want to be able to operate in the presence of processor failures. And that is an important consideration in this architecture. I'm also using the word permutation somewhat loosely. You can also provide broadcast every 200 nanoseconds, and this is one of the features that will make the GF11 actually suitable for a wider variety of problems than just the QCD problem. Let me now move on to the area of multi-purpose parallel processing. As I said in my introductory section, I believe this is a very important area, but I also believe that there are many open questions that remain to be answered. We are slowly answering these questions, but a lot of work remains to be done. How much parallelism is there in applications? What is the granularity of this parallelism? How should the parallelism be specified? Should it be specified explicitly? Should it be implicit in the language? Should it be derived by compilers? What are the appropriate resource management and scheduling approaches? For what class of problems do you need a global address space? For what kinds of problems will explicit message passing be good? What is the impact of communication latency and bandwidth on performance? And the bottom line really is what kind of performance can you sustain across what range of applications on a given architecture? As a community, we are making progress on these questions, but I believe a lot more work remains to be done. Now, 2 or 3 years ago, the situation, I believe, was as follows. We as a sort of technical community had done a lot of analysis and simulation to start understanding the answers to some of these questions. But what was really required was non-trivial prototypes on which we could run real applications and perform real measurements. Approximately 4 years ago, we started down the path of building a set of prototypes in IBM to start answering some of these important questions. I will come to the RP3 program in a minute, but before I get to that, let me mention that we also have a message passing parallel processor at IBM Research called Victor. A 32-node MIMD system has been operational since the middle of 1987. This is based on the NMOS transputer and is programmed using C, Pascal, Fortran, and Occam. Victor was and is a very quick and inexpensive approach to putting together a parallel processor very rapidly. It has been shown to be exceedingly good for a variety of applications where there's a huge amount of parallelism. Some of these applications are those that use Monte Carlo methods, ray tracing, and fractals. We are currently implementing circuit simulation on Victor and will use Victor as an experimental vehicle to study the area of message passing. A much bigger version of Victor will also be operational fairly soon. Moving on then to the RP3 program, our goal in 1984 was really twofold. One was to establish the feasibility of building a multi-purpose parallel processor out of conventional microprocessors. And the second, as I said, was to provide a set of tools for research on applications, algorithms, languages, and architectures. Here's a block diagram of the RP3 machine. In its initial formulation, RP3 was a 512-way parallel processor, and we have actually implemented 1/8 of this, a 64-processor version of RP3. Let me just very quickly go through some of the key attributes of this machine. First of all, we were really after a very, very powerful network, and the network is built out of the highest performance bipolar technology and package that was available to us in that time frame. The network was also, initially, the 512-way version was supposed to have combining. Combining basically lets you access a global memory location. That is, N processors can access a global memory location essentially in constant time for a given machine and not in order of N time, as would be the case without combining. We did not feel that combining was necessary as part of the 64-way machine, and so combining was not implemented in this version. So the first important characteristic of RP3 was the switch. The second important characteristic was the overall approach to managing caches and managing memories. So cache management was done under software control. Hardware mechanisms were not provided, but essentially data could be tagged as being cacheable or non-cacheable. The memory system was unique in the following sense. Even though the memory, the whole machine has a global address space, this address space can be broken up into a local address space and a global address space. And the amount of local and global can be changed dynamically at runtime under program control. So the two extremes of this would be to have all the memory configured as part of the global address space, in which case it becomes a true shared memory machine. The other extreme would be to configure the address space as pieces of local address space only without any shared address space, and in that case the machine becomes similar to a message passing machine. So part of the motivation for doing RP3 was to build a machine that was a flexible tool for studying various classes of architectures. A third important feature of RP3 was very extensive built-in monitoring capabilities. These monitoring capabilities allow us to measure things like the ratio of local to global memory access, the ratio of the cache hit ratios, instruction frequencies, delays caused due to network access, and so on. There's a processor as part of every one of these. There's a chip which is part of each processing element that gathers this data while the machine is executing. So these were some of the important features of the RP3 program. We also felt initially that it was important to get a level of performance high enough to make the machine interesting. And the initial levels of performance were to get roughly 1 billion instructions per second by the use of 512 processors. In addition to the hardware, there was a fairly extensive undertaking in terms of developing software and to develop tools that would allow us to, software tools that would allow us to experiment with parallelism. One of these tools is VM Epics, which allows experiments with parallelism on a 370 multiprocessor as opposed to the RP3. It was developed to allow us to do the necessary work in languages and applications while RP3 was being developed. As a side effect, this piece of software also provides real speed up on a 370 multiprocessor. And this has been operational at several sites. Together with VM Epics, we've also developed several tools which allow us to do post-mortem analysis of applications that are run under VM Epics in a parallel way. So what you can do is you can take an application, you can run it under VM Epics, you can gather trace information about the execution, and then you can run that trace information through various simulators and schedulers to try to understand what the effect of the switch would be and to try to understand what efficiency you would get out of an RP3-like machine. This particular slide is not important, but it shows the kind of information, or one example of the kind of information one can get out of VM Epics and these various tools that I described. Okay, to summarize then, I said earlier that we had two overriding goals for the RP3 project. One was to construct a multi-purpose parallel processor. And the features that make RP3 multi-purpose are listed on the slide. It uses a general purpose microprocessor. It's an MIMD structure. It has a very low latency, high bandwidth self-routing network, and it provides for flexible local and global addressing mechanisms together with a fairly general I/O subsystem that I didn't talk about. What makes RP3 an experimental facility are the system monitoring facilities, the fact that it uses standard operating systems, it has a Unix-based operating system, it uses conventional programming languages, and we have a fairly extensive suite of application development and analysis tools. The RP3 also has adequate system reliability to serve as an experimental facility. And I'd like to make two kinds of points. One is that this whole area is extremely important to our industry, and I see two, if I were to net it out, I see sort of two very important trends. One is the area of mainframe parallelism. Here we will construct the highest performance uniprocessors, and we will use parallelism to get performance levels beyond that possible with a uniprocessor. To a large extent, this will rely on advances in technology and packaging, and that's where the risk will be. To a large extent, mainframe parallelism will use evolutionary software. The other very important trend is the whole area of microprocessor-based parallelism, where we will use commodity parts and higher degrees of parallelism, and the key issue here will be sort of advances in software that will be required to make these efficient use of these higher degrees of parallelism. The second sort of summary comment I'd like to make is that parallel processing is important today. It's starting to be used, and I believe that this technology will be very pervasive in the future. This is one of the key systems issues that we have to address and we have to solve all the way from workstations to supercomputers. And I would also like to leave you with the thought that we are actively pursuing in IBM several different systems approaches. I've tried to identify and briefly explain most of these to you, and some of these are being pursued as products and some of them are in research. That brings me to the end of my talk, and I will now take questions.
And the first question from Gordon Bell at Arden Computer. Why did the GF11 and RP3 parallel machines take so long to develop, and what did you learn?
I think the basic reason why we have spent more time than we initially anticipated on both these machines is that they're both, in their own way, very complex, large systems. In neither case did we really exploit the CMOS building block replicated to produce a very high performance machine. The RP3 became complex for a variety of reasons. There was a significant amount of basic logic design that we ended up having to do. A lot of this was in the cache and memory system. We also ended up using multiple technologies and multiple power supplies, all of which contributed to the overall complexity of the machine. In the case of GF11 also, we didn't use a standard building block. We ended up building our own uniprocessors that were fairly significant in their complexity, and we ended up building a fairly complex interconnection network.
For myself, Gerald McGuire at Columbia University. For such calculations as used in QCD, where computations run for a long period of time, what is the reliability of the machine? What about the problem of detecting faults?
That's a very good question. As you probably know, the GF11 running, that the QCD computation is basically a fairly stable computation, and it's a Monte Carlo computation. In fact, the physicist on the project has always had the view that if you sort of randomly lost a bit once in a way meaning, let's say, once every day or every several hours, it wouldn't in fact significantly affect the computation. That's point one. Point two is that the GF11 is designed so that you can do a dump of the entire memory state of the system very rapidly. So you can dump the entire state in approximately 12 seconds. And therefore, one could very frequently checkpoint the system. So I think basically the way one will end up doing the QCD computation is either to do every computation twice and compare the answers, or to split the machine into two pieces and run the problem and compare processor by processor the results. That's how you would get your basic error detection. And with that, you would do two things. You would look at the errors and you would see if they were truly just random errors or there was some pattern. If there was a pattern, there would be a problem. Secondly, you could always back up and restart the computation because of this checkpointing capability. So I think we'll end up running the GF11, and it's architected to do that, basically split the machine in two and run the computation, identical computation on both sides, and compare the results of processors.